Part 2, hooray! Let's take a look at what happens if we try and reduce an acid chloride. If we use our standard reduction agent, the lithium aluminum hydride, and then water wash at the end, we have no way of stopping this from going on. Yes, the first step will get an aldehyde, technically speaking. I'm going to put it in brackets though. We get the aldehyde here, but it is very rapidly reduced, I don't know why I did 3 arrows there, to the alcohol. Nothing we can do to stop it using lithium aluminum hydride. So it's just going to keep on attacking until we end up with our alcohol. And then we'll go ahead and protonate it with the water wash at the end. So can't isolate the aldehyde. So the lithium aluminum hydride, as a very strong reducing agent, will get rid of our carbonyl completely and our leaving group. It'll replace it with 2 hydrogens. And then we'll protonate our alkoxide at the end. So, but if we want the aldehyde, we have to tweak our reagents a little bit. That's something we often do in chemistry, right? It's like, we know this thing does a similar reaction. We at least make this intermediate. But what do we do? How do we stop it there? Well, we've got to tame our reagent a little bit. Sodium borohydride is not strong enough to do this, but we can modify this lithium aluminum hydride a little bit. So if we use lithium aluminum OR3 hydride, having some alkoxy groups on the lithium instead, whatever those alkoxy groups happen to be, T-butyl is pretty common. If we do that, we will end up with our aldehyde. We can prevent this from happening. So we're still using H-. That hydride there is our nucleophile. This is, we can even highlight it in blue. That's our nucleophile, but it's being helped out by this whole big lithium aluminum alkoxide complex. Remember, H- by itself is not a nucleophile, it's a base. If we have the hydrogen on aluminum with other hydrides around, it's a very strong reducing agent. But if we go ahead and take, help that aluminum out a little bit, stabilize it a little bit more, we can kind of reduce the ability of that hydride to go nuts and react. And then so we're able to kind of tame it down and form the aldehyde instead. So that's great. So we can do our hydrogen nucleophiles now. So excellent. We can now go from carboxylic acid to alcohol, or I'm sorry. Well, yeah, we could go from carboxylic acid to alcohol, right? By converting it into an acyl chloride and then reducing it. Although we will see when we study acid chlorides directly acids directly that we can just reduce those. But turning the acid chloride to an aldehyde, that's something new. We have not seen that yet. So that's how we'll do it. We'll use a special lithium aluminum hydride that uses these alkoxides. And generally speaking, you'll see a lot of different ones. You'll see isopropyl as that R group in the lithium aluminum complex. You might see T-butyl. Those are pretty common. What about with carbon nucleophiles? We know that if we take an acid chloride and react it with a Grignard reagent, typically with ether, what happens is you end up making a tertiary alcohol. And I'm going to say R2 on this. You're going to end up putting 2 of your Grignards on. Because technically in the first step, you make the ketone, and then you do it again and make the alcohol then. So we have no way of stopping the Grignard. It's going to say, aha, acid chloride, excellent electrophile, here I go. making the ketone. Aha! Ketone, excellent nucleophile, electrophile. Here I go. Does the same thing, reacts twice, and we end up with our two of those carbon groups on. So whatever we happen to want to do, if we want to put both on, Grignard is a great choice. Again, assuming we have no acidic protons anywhere in our molecule. But this cannot be controlled. The ketone can't be isolated here. And so what did we do last time? When the hydride went crazy and completely reduced our compound, we tweaked the reagent. And so instead of using a Grignard reagent, if we want to make the ketone, we can do that using what's called a Gilman reagent instead. A Gilman reagent has copper and lithium and two of your R group, whatever you want to put on. We'll take a look at some actual examples of these. This is called a Gilman reagent. And in doing the Gilman, you will make your ketone. The copper and lithium are much more taming of your reagent than the magnesium and bromine are. So we will see that the copper is a little bit more stabilizing, and so we will only be able to react this to the ketone. So the acid chloride is much more electrophilic because we have the chlorine also withdrawing electron density than a ketone is. So the Gilman reagent will work. And this R2 is not indicating that it's a different R group. It means there are two of them. So for example, having two methyl groups, we'll put a methyl group on our molecule. I'll even write methyl. This is what's called a Gilman reagent. It is a more tame version. We will end up getting just the ketone here, unlike with the Grignard reagent. The Grignard reagent will go all the way to making the alcohol. The Gilman will stop at the ketone. Okay, and so we can look at a couple examples, right? So we have benzoyl chloride. Say we're going to put this with some ethyl Gilman. What we'll do is we'll end up making the ketone of these two. So we'll get rid of the chlorine, we're replacing it with an ethyl group. That's it. So replace your leaving group with the alkyl part of your Gilman reagent. And that's all you have to do. Ta-da! And now we've made our ketone. If we wanted to make the benzaldehyde instead, remember we're going to want to use something like lithium aluminum with an alkoxy group, H, and then a water wash at the end. You're going to make the aldehyde. So lots of reactions here. Let's do a quick review of them. So with reductions, use a super crazy reducing agent, go all the way to the alcohol. Use a tamed reducing agent, you'll get the aldehyde. So we can make alcohols and aldehydes. Hooray. Alternatively, if we wanted to make a ketone, or if we wanted to use a carbon nucleophile, if we want the alcohol with two new R groups on, and in fact, because this is so confusing, I'm going to go ahead and replace these with primes, just so we see that those R groups came from the Grignard reagent, and the Grignard only has one R group. That's the important part there. We have the ketone as the intermediate. We don't isolate it. It keeps on going until we make the alcohol with two new alkyl groups. If we do want to stop at the ketone, we want to use a Grignard reagent. I'm sorry, a Gilman reagent. Who decided these names should be so similar? Messed up. Damn scientists. So if you use the Gilman reagent, which is a dialkyl lithium cuprate, two R groups, they're the same. So two methyls, a copper, and then a lithium, put those together, you'll get a Gilman reagent, which you can get your ketone from by using an acid chloride. And just a couple of examples. So that's our reactions of acid chlorides. When we look at the rest of the reactions in this chapter, we'll see many of them will be very similar. And so we'll see those starting next with anhydrides.